Thank you, everyone, and thanks for being here for this talk today. Basically, I'd like to talk about the impact of deep learning into telecommunication, and I think the importance of this topic is like our industry and our vertical usually is not considered that much when it comes to these discussions. But today, I want to show you that how much this is important in our domain. So yes. My name is Hakimeh Purmehdi. I'm project lead and data scientist at Ericcson, Gaia team. Gaia is global AI accelerator and the organization within Ericcson, which is basically relates to how we are using machine learning and AI into wireless networks, communication networks that we work. Before joining Ericcson, I was with Microsoft Research, working on reinforcement learning algorithms, and I collaborated in implementation of a testbed for reinforcement learning. My background is in telecommunication, but after my PhD, I joined to AI/ML world and started a postdoc working with image processing and deep learning, and that was the start for me to come from telecom world to the AI/ML world. But today is not about my journey. It's about telecommunication journey. I like to start the story of like where we started, where we are, and where we are heading to. We started with first generation of wireless networks back in 1980s with a data rate of 2.4 kilobit per second. I guess it is funny now, but at the time we only wanted to transfer voice between two entities. Then we moved to second generation, and you can see suddenly we have a peak of 200 kilobit per second of data, and a service we have comes from voice to somewhere like data. If you remember, SMS or sending a text came to the services. And the journey moved on to 3G, which basically a new service of video call also added. That is era that we call it as like, it was the time that multimedia came, broadband system comes to the world of wireless communication. 4G, which basically I guess all of us have connected to that network, at least for last couple of years, was basically promised for data rate of 1 gigabit per second, and new services come to the equation. That was exactly the time that you started hearing about IoT. Sensors also added to the network. And we call this era of like the era of applications. Applications started to be introduced to the network. And we started moving from only connecting human to human to start thinking of like more than mobile phones, we can have other elements in the network. For example, sensors from IoT or machines from IoT. Now 5G is happening. Some of you have devices could connect to 5G. 5G is implementing since 2020. And as you can see, data rates increased, services increased. And basically in this domain, when we're talking about 5G, we're talking about digitalization of cities, industries, and our life. But the journey is continuing. Right now, in research domain, in companies like us, Ericcson, we are working on defining 6G. And with 6G, we are thinking of peak rates of 1 terabit per second. We're thinking of connecting different elements to each other. Let me give you what is our motto for 6G. 6G for us, not Ericcson only, for people from this domain, means that cyber-physical interaction. We are connecting not only human to human, machine to machine, and everything to everything. As you can see, beginning of latest version of 5G, which is expected to have XR into the domain, we're going to go beyond that. We're going to have AI almost everywhere and using methods like blockchain within the network massively. So having that said, you can see that how much new things coming generation after generation. But we have some challenges absolutely here, which one is like network management. With this huge amount of data, it is expected that new services brings complicated architectures. New services brings more nodes connected to the network. So managing such a complicated, congested network is not easy. And it requires a lot of considerations. Also, we have heterogeneous data. Back in 1G, 2G, 3G, the only data we had was like, for example, the data generated from your cell phones. But from 4G, we started to have data generated from like different sources. Sensors came, machines came. In future, you're gonna see your car is connected to the network. So the data is heterogeneous. How we deal with this data, it is very important concern that we need to challenge with, and the big data. Let me give you some numbers, and I ask, please do some calculations quickly. Every 1 millisecond, a single device in the network generates a bit of data. This data, I'm not talking about the traffic. Traffic means your call, your video streaming, whatever. No. Don't think about traffic. Just think about the data that your device generates every 1 millisecond in the network to say to the network that I am here. This data has average a size of 150 kilobit per second. So every single device, every 1 millisecond creates this data. 5G promised to have 200,000 of device per square kilometer. So just think about it of like every second of time, how much of data is generating in wireless network, and we need to deal with that. So we don't have just only big data, we have extremely big data, and we need to deal with this data. So, but we also know that big data has a good connection with deep learning. Deep learning and big data has a mutual connection with each other. Also, we know that deep learning showed a lot of good performance with some domains like pattern recognition, computer vision, signal processing, these stuffs. Recent works in this domain showed us that, in general, AI/ML solutions has a good impact into whatever we call in wireless communication as network function and network management. So combination of all of this shows that how much deep learning is important and is a promising solution for us to deal with our day-to-day challenges. Today I want to talk about this interaction between deep learning and telecommunication and tell you that how they are working with each other. Let's see first some of challenges, requirements we have, and benefits of deep learning. First is like, as I mentioned, our data is heterogeneous. It is noisy because you are transmitting it in wireless channel and many things affects. Even these lights can affect the channel. So everything affects this channel. Our bodies affects the channel. So this is the type of situation that we have for the noisy thing. And the data that we have necessarily wouldn't show trivial spatial or temporal correlation or pattern. But deep learning has this possibility to extract information and patterns from complex data. Also, we have this scenario of like extremely large data. And this large data cannot be stored like somewhere, because we need to collect this data from all over the network somewhere to process and stuff like that. But deep learning, specifically when neural network came to the equation, provide these concepts of batch processing and SGD, and that solved a lot of problem for us. We didn't need to collect this data from everywhere to a single place, to the central place, process that, and then create our model and transfer the model over the network. So that was one of the benefits of deep learning for us. Another benefit for us is, like, as I mentioned, the data is generating in the network is crazy huge. But it's not possible for us to go and label all of them. In most scenarios, we have unlabeled, semi-labeled data. Deep learning showed a lot of, actually we have a lot of effective solutions with deep learning that can work with non-labeled data or unsupervised methods. And also for network management, usually we have multitask scenarios. It is very expensive for us to train a model for each subtask to do a single multitask. Network functions usually are multitask scenarios. And deep learning shows us as, like, we can train a single model to go over a multitask solution, a multitask problem as a single model solution. So this is also another benefit of deep learning. Last but not least is, like, majority of the data that we have in mobile network are geometrical data. We have information about coordination of the UEs, network topology, graphs, network connectivity, all these things. This data could be called as, like, multivariate data. And one of the best solutions from AI domain to deal with multivariate data is deep learning. So all in all, we can see that deep learning has a lot of benefits for us in our vertical, but the point is, like, nothing comes for free or cheap. Deep learning requires certain system and software support, which is required to be provided in the network. Also, there are some other challenges. I would like to touch a bit on them to show that deep learning is not the perfect match for us, but it's a good match. One is, like, vulnerability to adversarial data. You know that how much deep learning relies on the data. Attackers could use from this feature to create or to design some artifacts to deceive the model and eventually push them to make a wrong decision. One goal for us is to make sure that the data that we are generating, the model that we are designing and implementing into the network is secure to such attacks. So this is one down point of deep learning that we need to consider. Low interpretability. Deep learning basically is very famous because it's some sort of black box. So we cannot necessarily clearly know that what is happening inside the model, inside this black box. In telecom domain, interpretability is critically important in a way that sometimes we sacrifice high accuracy to high interpretability because it's very important for our customers. They want to know what is happening because of the sensitivity of wireless networks. So this is another challenge that we need to deal with that when we are working with deep learning models. Data versus model. We know that how much data is important than model when it comes to deep learning. And I want to say that although we have a large of data, but we need to collect that data. We need to, train our model based on that data. Collecting this data is costly, is difficult. We need to find some solutions to deal with deep learning models, with this huge data, with some solutions that we don't need to centralize this data somewhere. I guess some of you know what I'm talking about, but I will go over that in just next slides. And the other thing is, like, privacy. Users sometimes are super sensitive about their privacy. Let me give you one example. Assume that we have a cell site covering a medical center, a military center, or a center with sensitive data. Usually these people wouldn't let us to collect their data. However, whatever they're doing in their cell affects the neighboring cell. So without having their data, doing anything, it's not possible to go to accurate model. How we deal with these privacy issues is another thing that we need to take care of that. Last but not least is like model limitations. Deep learning models usually are complicated, complex models. Fine-tuning of them is a big challenge. And we are working in an environment which is changing over the time. The exact moment that I started this presentation, the situation could be changed from this moment, which is like a few minutes after my presentation. So as we can see, we need to be able to adapt our models. Actually, I'm exaggerating. I don't want to say that in 15 minutes we need to update our model, but I want to say that our models sometimes in 24 hours require to be adapted. A rainy day is completely different from a sunny day. This year could be complicated, different from next year. So our model needs to be adapted frequently. So, but fine-tuning of a deep learning is a big thing. How we design these models in a way that they're efficient, they have their perfect performance, but actually in time manner situation. With 5G, there are three important categories that you may heard here and there. One is like we went to wider spectrum. We call it as like enhanced mobile broadband. We also started thinking about ultra reliable and low latency mechanism, which we call as, like I mentioned in the morning to one of the presenters, how you can react in less than 1 millisecond. A closed loop reaction in network for us is 1 millisecond or sometimes less than that. And when we are talking about low latency, we're talking about that numbers, how our algorithms can react in that closed loop latency. And massive machine type, I mentioned, for example, 5G says 200,000 of devices per square kilometer, so massive number of users there. Going to 6G, this story becomes even more complicated. I'm not going to over all of them, but just give you some examples. We need more secure and safe situations. We need a network could localize a single node with high accuracy. For example, in a smart factory, we need to localize a single element with the accuracy of 1 centimeter to 1 centimeter. Just imagine how much network should be reactive and accurate about localizing one element in a range of like, in a city or whatever, like that, centimeter to centimeter. In autonomous car, for example, it's important. It is extremely more low latency. Sometimes with 6G, we're thinking about less than microsecond. Less than 1 millisecond, a few microsecond sort of thing. Extremely large number of users, extremely large of throughputs and capacity. So this means that we need some enablers for deep learning, implementation of deep learning. One is fog computing. One is advanced parallel computing. Dedicated libraries for deep learning. Regular deep learning libraries sometimes fails to implement internet network. We are working to design dedicated libraries just for telecommunication and deep learning. Using dedicated libraries, distributed machine learning systems, and fast optimization algorithms. If you remember, I mentioned that collecting data centralized, it doesn't work for us. We need to think about edge computing, fog computing, and we need to think about distributed learning methods. I almost explained this one due to limited time I have. I will go quickly from that. So mobile devices has limited hardwares. Many of the deep learning algorithms are not possible to be implemented on the device. Mobile devices. We need to find solutions how to do deep learning methods considering these limited resources. Centralized doesn't work. We're thinking about distributed methods, we're thinking about edge computing, and we're doing our algorithms based on that. Mobile network environments are changing over the time. I explained to you. Sometimes these changes are super quick, sometimes are not. How we are adapting our model. Many of recent methods that we are thinking relates to the topic that you've may heard. deep, long life learning type of things, which means that over the time, the system tries to learn. Very similar to what a kid learns over its life to be grown up and gradually learns from the environment, from every experience, etc., etc. That's some of the mechanisms. And virus attacks and the concepts of anomaly detection is also very important for us. Attacks are changing again over time, like our environment. So could we go for any attack from the scratch, train, and adapt the model? It's impossible. We need to learn from what we did and experienced before. So deep transfer learning is one of the concepts that we are working when it comes to attack, anomaly detection, and security mechanisms. Having that said, we have a lot of different type of problems, challenges in wireless network. Here I try to cluster them in a bit. I hope that I'm successful in doing that, from like app level mobiles, mobile network applications, user mobility, network security, network control, how we can connect node A to node B, how we can steer the traffic through the network, how we can make this traffic reaches to the peak throughput that we are requiring, about the latency, etc. So we have these different categories of problems. Each of them have some examples. It's not limited to this. So you can say that a lot of problem, and each problem has its own nature, its own data. There is no one type of deep learning solutions that can solve all our problems. As you can see, we need a wide variety of deep learning algorithms that we, based on the problem, based on the data we have, based on the goal we need to achieve, we go through them and try to get to them. So that is why, for example, in our team, we are working with various type of algorithms. You cannot see a data scientist in this domain is expert in just one major. Usually they have to be expert in at least a few majors, because the challenges day-to-day they're working is different, is complex, and sometimes requires complicated solutions or merging of different solutions. This is an example. Ericcson, first of all, has a high record in literature and in research domain, as well as you may know that this company is the most important telecommunication infrastructure manufacturer in the world. Ericcson has a full record of creating these standards, these protocols, contributing to this domain from like research and state-of-the-art developments on the network, as well as the product. So a lot of patents and papers you can find under our company's portfolio. This is just an example of very recent papers published from my colleagues at Gaia Montreal office, which is one of the branches of Gaia. As I mentioned, Gaia, this is our team. We are not a very large team, but a lot of tasks and even things happening in this small team. I think it's more efficient team than like a large team. Gaia is a global organization. We have offices from India to North America, and in Canada, the only office is in Montreal. Thank you very much. I hope that I finished on time. If there is any question, I'm ready to take that.